I will show. So next step is to find out the area of tension reinforcement. So for that, as per G 1.2 page number 96, what it says we'll see. So this is the page number 96. The total area of tension reinforcement shall be obtained from the following equation. So we need to calculate the area of tension reinforcement by using this equation. AST is equal to AST1 plus AST2. So AST1 is area of the total tension reinforcement, and AST is the area of the total tension reinforcement. AST1 is equal to area of the tensile reinforcement for a singly reinforced section for MU limit, and AST2 is equal to AC into FAC divided by 0.87 Fy. By using this formula, we will calculate the AST2, and by using this, we will calculate the AST1. So we will see step by step. So AST is equal to AST1 plus AST2. This is given. This formula is given on page number 96. By using this formula, we will calculate the AST. For AST1, what we have to do is, there is one formula given on page number 96, G, that is 1.1a. So XU limit divided by D is equal to 0.87 Fy AC divided by 0.36 FCK BD. So both sides D is there, so cancel this and rearrange it. We need to calculate the AST. So AST is equal to 0.36 FCK B into XU limit divided by 0.87 Fy. After rearranging, so it comes. So our XU limit is equal to XU maximum. For that, XU limit divided by D is equal to 0.48. So I am moving D to here. XU limit is equal to 0.48 D. So substitute the D value. Simplify this. We will get 216 mm as our XU limit value. So by using this formula, we will calculate the AST1. So AST1. So substitute all the value. Our XU limit value is which we have calculated just now, that is 216. So substitute all the value. Simplify this. We will get our AST1 is equal to 1292.23 mm square as AST1. So call it as equation number 2. So now we will go for AST2. So for AST2, refer G 1.2. This formula is given on page number 96. So same formula I have written here. AC into FAC divided by 0.87 Fy. Substitute all the value. Simplify this. We will get our AST2 value is equal to 661.67 mm square. So call it as equation number 3. Now to find out the total tension reinforcement, substitute AST1 and AST2 value in equation number 1. So our equation, AST is equal to AST. Substitute AST1 value and AST2 value in equation number 1. After simplifying, we will get our AST value is 1953.9 mm square. This is our area of tensile reinforcement. This is the AST. So now assume the 25 mm pi bars. To calculate the number of bars required to carry this area of tension reinforcement. So now assume 25 mm pi bars. I am taking 25 mm. So area of 1 bar, that is small AST, is equal to pi by 4 into 25 square. This is the diameter. So substitute all the values. Simplify this. We will get 490.87 mm square area of 1 bar. After this, we will go for the calculation of number of bars. For that, we have the formula AST divided by area of 1 bar. So our AST value is, which we have got, is 1953.9 divided by area of 1 bar, that is nothing but 490.87. So simplify this, we'll get 3.98. So we cannot provide 3.98 bars, so I am taking it as 4 bars. After this we'll go for the calculation of AST provided. So for that we have the formula number of bars into area of 1 bar. So number of bars is 4. So area of 1 bar is 490.87. Simplify this, we'll get our AST provided is equal to 1963.48 mm square. So this is our AST provided. So now provide 4 numbers of 25 mm pi bars at tension reinforcement. So this is how we calculate the area of tension reinforcement and area of compression reinforcement. So I hope you understood. So next step is to calculate the design of shear reinforcement. Step 6 is design of shear reinforcement. For that, first what we need to do is we need to calculate the shear force. For simply supported beam, we have the formula VU is equal to WL divided by 2. So substitute all the values, simplify this, we'll get 163.25 kilonewton as shear force. So after this we'll go for the calculation of nominal shear stress, that is denoted as tau v. So to calculate this, as per clause 40.1 page number 72, what it says we'll see. So this is the page number 72, clause 40.1 nominal shear stress. The nominal shear stress in beams of uniform depth shall be obtained by the following equation. So we need to calculate the nominal shear stress by using this formula, that is tau is equal to Vu divided by B into D. By using this formula we will calculate the nominal shear stress. Let's see. So tau is equal to V divided by BD. So substitute all the value, shear force value which we have got just now, that is 163. Use 163.25 into 10 to the power of 3 and B is 300 and D is 450. Simplify this, we will get our tau value is equal to 1.20 Newton per mm square. So this is how we calculate the nominal shear stress. So after this we will go for the calculation of percentage of tension steel reinforcement, that is denoted as PT. So for that, as per page number 73, table number 19, we have the formula for so PT is equal to 100 into AST provided divided by B into D. So this formula is given on page number 72 and table number 19. We will get this formula. So substitute all the values. So AST provided, we need to provide the area of tension steel reinforcement here. So after this we'll get, after simplifying, we'll get our PT value is equal to 1.45%. So our PT value is 1.45%. So this is how we calculate the PT. After this we'll go for the calculation of tau C. By using the value of PT and FCK value, we'll calculate the tau C value. So as per table number 19 and page number 73, by using these two value, we'll calculate our tau C value. So our PT value is 1.45 and our grade of concrete is FCK 20 Newton per mm square. By using these two, we'll calculate the tau C value. So this is the table number 19. Design shear strength of concrete tau C Newton per mm square. So by using the value of PT, so why we need to calculate the percentage of tension steel reinforcement is this column has the value of percentage of tension steel reinforcement, that is PT. So that's why we need to calculate the PT value. So by using PT value and our grade of concrete, will calculate the tau C value. So our PT value which we have got is 1.45. So 1.45, where it comes, 1.45 means it comes in between 1.25 and 1.50. So for 1.50 we have the concrete value 0.72 for M20 concrete and 0.67 for 1.25 we have the concrete value 0.67 and for 1.50 we have the value 0.72. So we'll do the interpolation, we'll get the tau c value. So I have written here for 1.25 we have the concrete value 0.67 and for 1.50 we have the value 0.72. So now we need to calculate the what's the value of tau c for 1.45. So we'll calculate. So this is the tau c value. We have the tau c value. Tau c. So to calculate the tau c. So what we have to do is, so I will show the interpolation method. By doing interpolation we'll take first 0.67. So 0.67 why 0.67 means this value goes on increasing and this is the least value. We will take the least value. So I am adding it because it goes on increasing. After that we will take the greater value minus least value. So 0.67 plus 0.72 minus least value 0.67 and 0.15, the greater value minus least value 0.12 and the value which you want to find, that is 1.45 minus the least value, that is 1.25. So 1.25. So simplify this, we'll get our tau c value. We get our tau c value is equal to 0.71 Newton per mm square after doing interpolation. So this is how we calculate the tau c value by doing interpolation. I hope you guys are understand. So after this we'll go for the comparison of tau v and tau c. So next step is to compare the tau v and tau c. So our tau v value is 1.20 Newton per mm square and our tau c value is 0.71 Newton per mm square, which we have got. So our tau v value is greater than tau c value. So when our tau v value is greater than tau c value, so shear reinforcement is needed. So we need to calculate the spacing of stirrups and shear carried by concrete and shear carried by stirrups. So as per clause 40.4 page number 72, what it says we will see. So to design of shear reinforcement, when tau v is exceeds tau c given in table number 19, the shear reinforcement shall be provided in any of the following forms. So what they have said when our tau v value is greater than tau c, we need to provide the shear reinforcement in the form of maybe vertical stirrups or in the form of bent up bars along with stirrups, or one more they have given in the form of inclined stirrups. So where bend up bars are provided, their contribution towards shear resistance shall not be more than half that of the total shear reinforcement. Shear reinforcement shall be provided to carry a shear equal to Vu is equal to tau c Bd, the strength of shear reinforcement, that is Vus, shall be calculated by using this formula. So for vertical stirrups we have the formula Vus is equal to 0.87 Fy ASVD divided by SV. This will come to this later. Now we will calculate the shear carried by concrete by using this formula. So now we need to calculate the shear carried by concrete, that is VUC is equal to tau c into BD. So shear carried by concrete is equal to, substitute all the value, 0.71, or B value is equal to 300 and D value is equal to 450. So after simplifying, we'll get our value is 95.85 kilonewton is our value. So now we need to calculate the shear carried by stirrups. So shear carried by stirrups is equal to Vu minus Vuc. So substitute all the value, simplify this, we'll get answer as 67.4 kilonewton. So after the calculation of shear carried by concrete and shear carried by stirrups, so we need to go for the calculation of spacing of stirrups. So spacing of stirrups should be calculated. So by using formula Vus is equal to 0.87 Fy ASVD divided by SV. So this formula is given on page number 73. So we need to calculate the spacing of stirrups. No. So I am moving SV is equal to here and taking this to here. Rearrange. So I have rearranged this, and after that, for calculation of SV, we need to calculate the ASV. So for this, I am assuming two-legged vertical stirrups of 8 mm pi bars. So our ASV is equal to 2 into 4 by pi by 4 into a square. Simplify this, we'll get our ASV value as 100.53 mm square. So after this, substitute this value in this equation. So substitute all the value, simplify this, we'll get our spacing of value is 242.33 mm. So I'm taking the approximate value. So 225 mm. And after this, there is one more criteria they have given on page number 47 and 48. We'll see what they have said. So this is the page number 47. The maximum spacing of shear reinforcement. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 D for vertical stirrups. What they have said our spacing of stirrups should not be greater than 0.75 D for vertical stirrups, and D for inclined stirrups at 45 degree, where D is the effective depth of the section. In no case shall the spacing exceed 300 mm. So what they have said our spacing of stirrup should not be greater than 300 mm. So we'll see. Our SV value should not be greater than 0.70. So D value is 450. Substitute all the values. Simplify this. We'll get our SV value as 337.5 mm. So collect as equation 2. So in case 3, our SV value should not be greater than 300 mm. So 300 mm. So our SV is equal to 300 mm. So what they have also mentioned, our SV value should be least of these three. Case number 1, 2, 3. Our SV value should be least of these three. So which is this? Our 225 mm is the least value. So I am taking our SV value as 225 mm. So whenever you are designing this, though if you get the value less than 300 mm, that is 250, 150, 260, less than 300 mm, you can provide that value. So but in sometimes whenever it is coming greater than 300 mm, that is 400, 450, 500, at that time you should provide the 300 mm, the least value, because the spacing of stirrups should not be greater than 300 mm, they have mentioned. So I am taking our SV value should be least of the above these three equations. So 225 mm is the least value. So I am taking our SV value as 225 mm. So provide two-legged vertical stirrups of 8 mm pi bars at distance of 225 mm center to center. So this is how we calculate the spacing of stirrups. I hope you understood. Next step is to drawing of reinforcement details. Without the drawing, our problem is incomplete. So we'll see. So this is the beam having the suppose 500 mm and clear span of 6000 mm and effective span of 6450 mm, and the depth of the beam is 500 mm. So this is the simply supported beam. So 4 numbers of 25 mm bars at tension reinforcement, it comes bottom, and 3 numbers of 20 mm pipe bars as compression reinforcement, it comes on the top, and 2 legged vertical stirrups of 8 mm pipe bars at distance of 225 mm stirrups, and these are the vertical stirrups. So this is the longitudinal section diagram of our beam. So now this is the cross section diagram of cross section diagram. So when you cut the beam here or here, so we'll see 3 numbers of 20 mm pipers at top side and 4 numbers of 25 mm pipers at bottom side. So the overall depth of the beam is 400 mm and our width of the beam is 300 mm. So this is the reinforcement details, and here our problem ends. I hope you guys are understood. So if you like the video, if you understand the video, like it, share it and subscribe for the more videos. Thank you for watching.